question number 5, dancing a slinky. The problem statement says, twist a slinky several times and keep it bottom fixed. After releasing the top, the slinky starts to dance, wave-like phenomena that we can observe from the side view. This is an overview that what you're going to do in this presentation. At first, a phenomenon demonstration, then the key observation, theoretical model, our setup and experiment results, and a conclusion at the end. Twisting the slinky adds potential energy between the coils. When the slinky is released, initial force generates motion, creating the torsional, longitudinal, and transfer waves. This 3D parametric plot highlights the coupled oscillatory behavior of the system. When the slinky is released with its fixed bottom, a controlled boundary condition is created, allowing for precise analysis of its wave dynamics. This prevents external motion, ensuring that the observed behavior is purely due to torsional and longitudinal wave propagation. Twisting the slinky adds potential energy between the coils. When the slinky is released, initial torque generates motion, creating the torsional, longitudinal, and transfer waves. The spin constant and elastic restoring force influence how the slinky rebounds, contributing to its oscillatory motion. Over time, damping reduces the motion, gradually bringing the system to rest. So one of the most important parameters in the slinky is the angle of twist that represents the number of twists. We have the number of coils and also the diameter, that these three have a relationship. When we twist the slinky, we add more coils on it, and also these create a compression that decrease the diameter. We have the diameter and mass that affect on the moment of inertia. Also, we have the diameter of each coil, and we have the length that can affect on the stability, and also the material. Here, we model the slinky in cylindrical coordinate instead of Cartesian coordinate, as this improves the accuracy of radial measurement and simplifies our equations. Wave propagation in dancing involves several energy transfer. Initially, the compression of potential energy longitudinal wave travels through each coil. The torsional wave observed from above or side view cause the slinky to rotate. Meanwhile, the transfer waves generate the left and right motion, illustrating the complex interaction of wave types in this dynamic display. Here, in a normal spring, F equal minus Kx arises from linear displacement. For torsional spring, this formula shows the rotation, and slinky's stiffness measured by the torsional spring formula, because we have the angle and the rotation in our slinky's model. As the slinky begins to dance, each oscillation consists of a compression phase where the coils move closer together due to the restoring force. The right side of the equation is going to be negative, and an expansion phase, the following formula is going to be positive. Also, we use these relations for calculating the torque due to the angle we have in the slinky. By these following formulas, I calculate the torque, I to the double dot, as a function of time. Here, for finding the angle of each coil, we divide the changes of our angles with the number of coils. And here, we have the I, we have the I and R that represent the radius and represent the mass of one coil. And this formula shows the period of each oscillation when the slinky released. With the past equations, we measure that how much time is taken to with the past equation, when a slinky released with this equation, we measure the time is taken to rotate through an angle. And this is our method that how we calculate a single coil for the slinky. This is a simple torsional oscillation oscillator equation, that this term represents the rotational inertia, that I is the moment of inertia of the slinky segment, and we have this Newton's second law for rotational system. That's alpha here represents the theta double dot. Here, this term represents the damping, where we have this C, that is damping coefficient. We have the air resistance, friction, and viscoelastic damping in the material. This term represents the elastic restoring force, or Hooke's law, that we have the equation here. We have the theta dot, that is the first derivative of theta, that represents the angular velocity, and the second derivative of theta, that represents the angular acceleration. Here, I represent the amplitude of oscillation, and here I represent the amplitude of angular displacement. Here we have the function of time at the end of our equations. As I mentioned, this is the main formula for moment of inertia, which we modified it into this because we have the radial variation, and so we expressed it as a function of time. In this video, we can see that we have the radial variation. We try to find the new radius with this formula, where here r prime is our new radius. We use these relations for friction, but in our experiments we didn't measure the friction because it's too minimum, and between each coil is linear, but overall is not. Here for elastic limit it means that the maximum number that we can twist the slinky. If you see this slinky is deformed completely, it's not on the first, it's not in the shape of the first time. By these formulas and in our experiments, I try to draw this graph where L here represents the number that we twist the slinky. Okay, this is a summary of our theory. And for experiment setup, I attach a rotating motor under this black box. I use a controller and a battery to make the motor spin. I also use a different size of rods for different slinkies. And I placed one rod vertically inside the slinky and one another horizontally. I used a solid joint to connect these two rods to each other, and one of them to the motor. Here you can see that the horizontal rod that attached in the slinky, it completely rotates the slinky in the way that I could measure the angle of twist. A light was shining from above, and when the paper fell onto the marker, onto the mark that I put there, it means that it completely twists one time. I actually used a toggle clamp, but it had a lot of errors in my experiments for releasing. The rubber band shows the better results in our experiments, as a scissor also has instead of a razor. For the fixed bottom, we used duct tape. We completely fixed one coil onto the box. There was a 3 centimeter wood base under the box, so it completely didn't move at all. For recording our experiments, I put a 90-degree camera in front of the slinky and a camera on top for see the radial variations. For experiment setup, I divide the slinky into 3 parts: a top, the 2/3, and a 1/3 at the end. Here our experiment that shows the 3 times twist, the angle over time. As I mentioned, the 3 parts of our slinky. This is my theory versus experiment. I calculate each oscillation in the period. I calculate the period of each oscillation on my experiments graph. Also, I have the graphs from different times of twist, as you can see there. This is the theory versus experiment for this graph. I have the one-time twist for this slinky, and for other slinkies, I did the same thing. This is for biggest one, and also I have this graph that the first one shows the one-time dance, the second part shows the dancing time, and the blue part shows the points that the slinky completely rebounds. Here we have the collapser. Here the oscillation didn't rebound because the damping is getting, because the damping is coming. Here and here you can see that damping from the stability. As you can see, this slinky completely collapsed. As the slinky length increased, the stability also, you can see the result. For a conclusion, these are my formulas and equations that I use. This is my experiment that I divide the slinky in 3 parts. And this is a theory versus experiment where my theory completely supports my experiments. These are my references, and thank you for attention.